Hey, I've been thinking about how the Earth spins really fast, like 1,000 miles per hour at the equator. But why don't we feel it? Shouldn't we be all dizzy, like when you're on a merry-go-round that goes super quick?
That's a great question. It's one that trips up a lot of people at first. Imagine you're on that merry-go-round, and it starts slow, then speeds up. You feel dizzy because it's accelerating, pushing you sideways, and making your body want to lag behind. But the Earth? It's been spinning at that steady speed for billions of years, without ever slowing down or speeding up in a way we notice. At the equator, yeah, it's about 1,000 miles per hour. But since everything, you, me, the air, the oceans, is moving right along with it at the exact same constant speed, there's no sudden change to make us feel woozy. It's like being inside a smooth train that's already going full tilt. You don't sense the motion unless it jerks or turns sharply.
So because it's always spinning the same way, we just match it? But merry-go-rounds spin too, and they make you feel it right away.
Exactly. You match the Earth's spin from the moment you're born. Think of it this way. When you jump rope in the backyard, you're moving with the ground under your feet, even though the whole planet is turning. The merry-go-round feels different because it starts from zero and builds up speed. That acceleration is what tugs at your stomach and makes the world blur. Earth's rotation is constant, no acceleration, so no dizziness. Scientists call this inertia. It's that tendency things have to keep doing what they're already doing unless something pushes them otherwise. We've all inherited that spin from the Earth itself.
Inertia. Like when a ball keeps rolling until it hits something? Okay, that makes sense for why we're not flipping around. But if the Earth's going that fast all the time, why doesn't the spin just, I don't know, make everything slide off the edges or something?
You're getting right to the heart of it. Since the speed is steady, we don't feel flung around. But yeah, there is this outward pull from the spin that you might wonder about. What keeps us from sailing off into space like we're on some giant top that's whirling too wildly?
Yeah, exactly. If it's spinning so fast, shouldn't we feel like we're being thrown away from the center?
That's a smart follow-up. The spin does create a kind of outward force. It's called centrifugal force, which tries to push things away from the axis of rotation, like water flying off when you swing a wet towel around your head. On Earth, at the equator, that force is real, but pretty weak compared to something else pulling us in. We've got gravity doing the heavy lifting there, keeping everything hugged to the surface. But let's dig into how those two balance out, so we're not going anywhere.
Gravity? Like how it makes apples fall? So it's stronger than the spin's push?
Spot on. Gravity is that invisible tug from Earth's mass, pulling everything toward the center, no matter how fast we're rotating together. At the equator, the centrifugal force from the spin is only about 0.3% as strong as gravity, so it barely nudges us. That's why you weigh a tiny bit less there than at the poles, but you don't notice it flying you off. It's all in perfect harmony because the Earth formed this way, with its spin and gravity working as a team. Remember that towel? If you swing it slow, the water stays put. Crank it up too fast, and it flies. Earth is spinning just right, not too fast to overcome gravity.
Oh, I get it now. So the constant spin means no dizziness from speeding up, and gravity handles the rest to keep us stuck. But wait, if I'm jumping up in the air, wouldn't the ground spin away from me while I'm up there?
You're really piecing this together. Jumping is a perfect test. When you leap, do you land back on the same patch of grass, or does the world scoot out from under you?
I always land in the same spot. But how? If the Earth's moving so fast...
Because you carry that spin speed with you when you jump. It's like tossing a ball straight up in a moving car. It comes right back to your hand, not smacking the back window. Your body, the air around you, everything shares the Earth's rotation. So when you come down, the ground hasn't left you behind. No sliding or spinning away.
That clears it up. So we don't feel it because it's steady and we're part of it. But if I dropped a ball from a tall tower, would it land straight down or curve because of the spin?
Great thought. Actually, it does curve a tiny bit due to the Earth's rotation, called the Coriolis effect, which is why hurricanes swirl. But from a tower, it's so small you wouldn't see it. The key is that shared motion keeps things predictable.
Cool. I never realized how sneaky that constant speed is. Makes me wonder what it'd be like if the spin suddenly stopped, though.
That'd be chaos. Everything would keep going at 1,000 miles per hour while the ground halted. But luckily, it's not stopping anytime soon. What do you think holds it all in balance so we stay put?
I guess it's that inertia thing you mentioned. It keeps everything moving together without needing to push or pull all the time.
Exactly. You've nailed it. Inertia is like the lazy rule of the universe. Stuff keeps going at the same speed in a straight line unless something messes with it. But on Earth, that spin isn't a straight line. It's a big circle. But because the planet is so enormous, it feels steady, like a super long, gentle curve. To really get why we don't feel any of it, picture yourself in a car on a straight, empty highway at night. The speedometer says 70 miles per hour, but inside you're chilling, reading a comic book, maybe munching snacks. Why no whooshing wind or stomach flips? Because the car, you, and everything inside are all cruising at exactly that same speed. No one's getting left behind.
Yeah, like when my family drives to Grandma's house. It feels totally still until we hit a bump or turn onto a curvy road.
Bumps and turns, that's the key. In a car, you only feel the speed when it's changing. Speeding up from a stoplight shoves you back into the seat. Braking yanks you forward. And whipping around a corner makes you slide sideways. That's acceleration messing with your inertia. But once you're at a constant speed on that straight stretch, zilch. No dizzy spells, no flying snacks. Earth's spin is like that endless highway ride, but wrapped around a globe. At the equator, we're all locked into that 1,000 miles per hour eastward zip from the get-go. Your body, the trees, even the clouds overhead. Billions of years of the same smooth loop means no starting, stopping, or sharp bends to jolt us. The planet's size makes the curve so wide that the pull to keep circling is tiny, way less noticeable than a car's turn.
So it's not just constant, it's constant in a huge way. Like, if Earth was smaller, would we feel it more? Like on a bike going around a tight loop?
Smart connection. Yeah, size matters a ton. Imagine shrinking Earth to the size of a basketball spinning in your hand. That'd be wild, with stuff flying off because the curve is too tight for inertia to handle easily. But our real Earth is 8,000 miles across, so the rotation speed spreads out over that massive distance. It's like comparing a kiddie carousel where you feel every whirl to riding an airplane in a smooth loop-the-loop at 30,000 feet. You barely notice because everything's scaled up. Astronauts in space stations that spin to fake gravity say it's the same. Once you're matching the spin, it feels normal, no queasiness. That's inertia at work, gluing our motion to the planets without fanfare. We've been strapped into this cosmic car ride since the Earth cooled and started turning, passing that speed down like a family heirloom.
Heirloom? That's funny. So even the air we're breathing is spinning with us? No wonder birds don't get blown away when they fly.
You got it. Birds, planes, raindrops, all tuned to the same rhythm. If a bird took off straight up, it wouldn't suddenly lag behind like in a bad cartoon. It'd keep that eastward push and land right where it aimed. It's all because inertia matches us perfectly to the spin, turning the whole setup into one big, steady system. No extra effort needed to stay in sync.
Wow. I can almost picture sitting in that invisible car now, just rolling along with the world. But if we're all going that fast together, what keeps us from getting squeezed or tossed out toward the sides anyway?
Ah, that's the million-dollar question. Being tossed out or squeezed sideways. It's not inertia alone handling that. There's a sneaky outward tug from the spin itself trying to fling us away. Like when you're on a playground spinner and let go of the bars. But something way stronger yanks us back in every time. Ever wonder what that counterforce is? The one that makes sure we don't go sailing off like loose change from a pocket?
Yeah, like in those videos where kids get thrown off if it spins too wild. Is it wind or something holding us down? No, that doesn't sound right.
Wind's part of the team, but not the captain. The real boss is gravity, that constant pull from Earth's huge bulk drawing everything toward its center, like a giant magnet for your shoes. Picture the planet as a massive ball of rock and metal, all crammed together, creating this invisible grip that keeps the atmosphere, oceans, and us pinned to the surface. Without it, we'd float off into space, spin or no spin. But with the rotation, that adds a twist. Literally.
So gravity's pulling us in, but the spin's pushing out? Like they're fighting?
Exactly. Like a tug of war where gravity's the unbeatable heavyweight champ. The spin creates what's called centrifugal force, that outward shove you feel on a fast merry-go-round, or when your mom takes a corner too quick in the car, pressing you against the door. At the equator, where the spin's fastest, this force tries to hurl you eastward and away from the axis, like a slingshot letting loose. But gravity? It's pulling downward with about 300 times more oomph, so the centrifugal push barely registers. It's why you can stand at the beach without your toes curling for dear life. The balance is so spot on that the net effect is us staying put, feeling solid as a rock.
300 times? That's huge. So even at 1,000 miles per hour, it doesn't budge as much?
Right on the money. Think of it like swinging a yo-yo. If you twirl it slow, the string stays taut, keeping the yo-yo close. Crank it faster, and the string strains but holds if it's strong enough. Earth's string is gravity, forged from its enormous mass, over 6 sextillion tons of it, all yanking inward. The centrifugal force from spinning once every 24 hours is puny by comparison. It only lightens your weight by a fraction of a pound at the equator. That's why climbers on Everest or surfers in Hawaii don't feel any different. They're glued down tight. Scientists measure this balance with pendulums and scales. Foucault's pendulum, for instance, swings in a way that shows the Earth's turn without us feeling flung.
A pendulum? Like the ones in old clocks? Cool, so it proves gravity wins the fight every time.
Yep, those very ones. Named after a French guy who used it in the 1800s to show the planet's rotation without any dizziness. The pendulum keeps its swing path steady while the Earth turns underneath, but gravity ensures it doesn't wander off course. Without that pull, the spin would scatter everything like confetti at a party. But because gravity dominates, we get day and night, seasons, and a cozy ride. It's this inward hug versus the outward nudge that lets life thrive. No one getting slingshotted into orbit by accident.
I like the yo-yo idea. Makes it less scary, like the string's always got our back. But if gravity's so strong, holding us even when we're spinning, what if I tried to jump up high? Would I still come down right where I started?
Jumping's a fantastic way to test it. Let's think about what you'd really experience up in the air.
Okay, so if I jump up, does the ground just zoom away under me because it's spinning so fast? Like, wouldn't I land way over there?
That's the classic worry. Plenty of folks picture it that way, like the Earth's rug getting yanked out from under your feet mid-leap. But nope. You land right back on the same spot every time. Why? Because when your feet leave the ground, you don't suddenly stop spinning with the planet. You keep right on going at that same 1,000 miles per hour eastward speed. It's your shared velocity, that matching speed from inertia, that tags along with you into the air. Just like a helium balloon in a moving bus doesn't drift to the back.
Shared velocity, so I'm still zipping around with the Earth even when I'm not touching it?
Precisely. Think about jumping on a moving skateboard. If you're cruising along a straight path and hop up, do you plop down on a different board behind you? Nah. You stay put relative to the skateboard because you're both moving forward together. The Earth's spin works the same. The ground, you, and the air are all in this synchronized dance. When gravity pulls you back down, the spot you jumped from has traveled the exact same arc around the planet's axis as you have. No zooming away, no wild chase, just a smooth return. Experiments with high-speed cameras on jumping athletes show this perfectly. Their landing spot doesn't budge sideways from the spin.
That skateboard thing helps. But what if I jumped really high, like from a trampoline or something? Wouldn't the spin curve more while I'm up longer?
Even from a trampoline, or, say, a tall building, you'd still come down where you expect. Give or take a tiny nudge from other stuff like wind. The time you're airborne is so short compared to the Earth's full 24-hour spin that the ground only moves a fraction of an inch relative to you. At the equator, in 1 second of jumping, the Earth rotates about 15 inches. But since you're rotating too, it cancels out. Pilots dropping supplies from planes see this. The packages land near the target because everything shares that rotational speed. It's not magic. It's physics, keeping the party together.
Inches? That's not much at all. So no matter how high, as long as it's not space high, I stay matched?
You got it, up to a point. For everyday jumps, yeah, spot on. But let's say you're in a helicopter, hovering over a fixed point on the ground. The chopper has to keep drifting eastward at that 1,000 miles per hour to stay above the same spot. Otherwise, the Earth spins away below. If you jump out, don't try this at home, you'd fall straight down relative to the chopper because you're all synced. Astronauts training in zero-gravity simulators learn this too. They practice maneuvers assuming the shared spin until they detach completely into orbit, where things get weirder.
Helicopters, drifting... Whoa, I didn't think about that. So even birds flapping around don't get left behind when they take off?
Exactly right. Birds launch with that built-in spin velocity, so they soar relative to the ground without the planet pulling a fast one on them. A falcon diving at 200 miles per hour is adding its speed to the Earth's rotation, not fighting it. Drop a feather from your hand, and it flutters down nearby, not miles west, because the air around it is also spinning along. This shared motion is why sports like basketball or soccer work seamlessly. The ball follows the same rules as you do, curving only from kicks or throws, not the planet's turn.
Feathers and birds make sense now. I guess that's why no one ever talks about the ground sneaking away during games.
Nope. Coaches would go nuts if that happened. It's all thanks to that inertia we talked about earlier, preserving your motion until gravity reels you in. Without it, jumping would be like trying to hop off a speeding train. You'd tumble behind. But on Earth, we're all passengers in the same steady vehicle, so leaps stay local. Scientists even use this in labs with rotating platforms. Spin a table fast, toss a ball up from it, and it lands back on the mark, because velocities match.
Rotating tables sound fun to try. Okay, I think I've got the jumping part. We stay put because we're all spinning together. But now I'm curious. How do we even wrap our heads around something this huge and sneaky that we can't feel at all?
Wrapping our heads around it is half the fun. There are some neat tricks to visualize this invisible whirl without needing a spaceship.
Yeah, like How do you even picture something that's always there but totally invisible? It's kind of mind-boggling.
It is tricky at first. Everything feels so still under our feet, right? But that's where our imaginations come in, like detectives hunting for clues. One easy way is to think back to those car rides we talked about, but zoom out super far. Picture yourself as a tiny speck on a giant beach ball that's slowly turning under a bright light. From your spot on the ball, the sand doesn't rush by. You just see the shoreline curving away gently. That's Earth. Its hugeness makes the spin feel like a lazy afternoon drift, not a roller coaster. No dizziness because the road is curved so wide your eyes can't catch the edges blurring.
A beach ball. Okay, that helps a little, but I'd have to be really small to see it like that.
Exactly. And that's the point. Scaling it down in your mind tricks your brain into getting it. Or try this. Grab a globe from school, or imagine spinning a basketball on your finger. Watch how the lines painted on it zip around. But if you glued yourself to the equator with tape, you'd feel steady, while the room outside whooshes by. That's like us on Earth. The tape is inertia and gravity, holding our view steady so the stars and sun seem to move instead. Real globes in museums even have motors to mimic the day-night cycle. Spin one, and you'll see how towns at the equator blur fastest, but a tiny figure standing there wouldn't wobble.
I've spun a basketball before. Yeah, the equator part goes quickest. So if I was that tiny figure, I'd think the basketball was still and everything else was moving.
Spot on. It's all about your frame of reference, what you're glued to. Another cool way is peeking at space views, like those videos from the International Space Station. Astronauts float up there and watch Earth twirl below like a blue marble in slow motion. From orbit, you see hurricanes swirling and continents sliding into view, proving the spin's real. But down here, we're too close, like ants on a record player who don't feel the groove. Apps on your tablet can simulate that too. Tilt it and watch clouds race eastward at 1,000 miles per hour, yet no one's tumbling off.
Space station videos are awesome. I saw one where the Earth looks like it's rotating under them. But why can't we feel that from the ground, even with all these pictures?
Because we're embedded in the motion, like fish in a spinning aquarium who think the water's calm. To imagine it better, try a thought experiment. Close your eyes and pretend you're in a dark room on a smooth merry-go-round that's already spinning at top speed, no starting jolt. Open your eyes, and the walls look fixed. You toss a ball, and it arcs normally. That's Earth. Our room is the atmosphere and ground, all whirling together. Or, build a model with string and a ball. Tie a weight to a string, swing it in a circle overhead. The weight flies straight out, but if you add a strong inward pull, like gravity, it stays in orbit. No flying off, just steady circling. Kids in science clubs do this with homemade setups. Add lights for day and night, and suddenly the spin clicks without any queasy feelings.
The aquarium fish. That's perfect. I bet if fish could talk, they'd wonder why the castle moves too. So these models show it's all connected?
They do. It's like piecing together a puzzle where every bit moves as one. One more trick. Watch a time-lapse video of the sun crossing the sky. Flowers open, shadows shrink. All because we're turning toward the light at that steady clip. No need to feel the speed. The evidence dances right in front of you. Pilots and sailors have used star patterns for centuries to track the rotation without sensing a thing. It's invisible, but everywhere, shaping our days.
Time-lapse. Yeah, like those flower videos where everything speeds up. It makes the Earth's turn seem real without the whoosh. I think I'm starting to see it now. Not feel it, but picture how we're all riding this giant, smooth wheel together.
You've got the hang of it. It's that blend of big-picture views and small-scale play that unlocks the mystery. The spin's there, steady and huge, but our lives fit right into its rhythm, like a well-worn path. No dizziness, no flying off, Just a world that turns, so we can chase sunsets and count stars. Pretty amazing how it all balances out, huh?
It really is. Thanks for helping me wrap my head around it. I won't look at jumping or car rides the same way again.